This week, we bring you an Arizona Illustrated special, 100 Years in Space. First, focusing the universe.
Science was to change dramatically in the years following the dedication of Steward Observatory.
Desert Moon.
Okay, I'm separating from the spacecraft.
The Phoenix Mars mission. And OSIRIS-REx, images from space.
Is this Tucson?
Welcome to Arizona Illustrated. I'm Tom McNamara. It's an important and exciting time in space exploration. And tonight, as we reflect on the last 100 years, we'll be sharing excerpts from original documentaries by filmmakers from right here in southern Arizona. Now, humankind has been looking to the stars for thousands of years. Ancient sailors used them to find their way at sea, and early astronomers like Aristotle and Galileo held their gaze on the heavens in hopes of unlocking the mysteries of the universe. Here in Arizona, visionary pioneers of space exploration in the modern age have been at the forefront of understanding our place in the universe. And for them, the Steward Observatory at the University of Arizona allowed them to see what had never been seen before.
The roots of modern astronomy in Arizona stretch back 150 years to a chance encounter between two New Englanders, one of whom was consumed by the desire to find life in space. Percival Lowell was born to a wealthy Massachusetts family. A graduate of Harvard, he thought of himself as an astronomer.
He had a lot of money, and he was interested in the planet Mars. And in those days, if you had the money to build your own observatory, you became an expert in that field, no matter what your educational background was.
The other New Englander was Andrew Ellicott Douglas, a 28-year-old with a bachelor's degree in physics.
So he hired the young Douglas to come out to the Arizona Territory to find a location for his telescope and to build the observatory.
Flagstaff is where the first major observatory in what was then the Arizona Territory was built. Douglas oversaw the construction of and helped build Lowell's Observatory.
You know, the world was smaller and the science enterprise was smaller and people weren't as specialized, and it was a kind of wild frontier, so, you know, you had to make it up as you went along.
Arizona, in its early days, picked up rugged individualists. They decided what they wanted to do and they got out and they did it.
Lowell would come out from time to time and make observations, but it was basically from 1894 to 1900, A.E. Douglas ran the Lowell Observatory.
At the turn of the 20th century, conventional wisdom held that there was a civilization on Mars.
There were Martians because Mr. Lowell said so, and he had the biggest telescope that was looking at Mars.
Douglas would draw by hand what he observed on Mars. Lowell used these sketches to create his own imaginative drawings of Mars.
And then he came up with an entire story of a dying civilization on a planet in a desert-like state, and canals are brought down from the ice caps of Mars to bring water to the Martian civilization. And of course, some of the articles published by Lowell would inspire H.G. Wells to write The War of the Worlds.
One winter night, Douglas observed unusual activity on Mars. This was the sighting Lowell had long hoped for.
Douglas was at the telescope in Flagstaff observing Mars. Douglas saw something that looked like a wisp, like little wisps.
For Percival Lowell, those wisps were proof of life on Mars. But to A.E. Douglas, they proved nothing. Douglas publicly disagreed with Lowell and lost his job.
Douglas was basically fired for being a good scientist.
Jobs in professional astronomy were not abundant in those days. At the age of 40, A.E. Douglas took a job at the University of Arizona and began a new career teaching geography and physics. From the moment Douglas arrived in Tucson, he wanted to build an observatory that rivaled the Lowell Observatory in Flagstaff.
There were only 3 larger telescopes in the United States. So he was trying to do something fairly substantial.
In those days, you realized that the federal government or any sort of government entity didn't start funding basic science until after World War II.
Because neither the university nor the state were interested in funding the proposed observatory, Douglas turned to private donors.
In October of 1916, they were able to announce to the press that Mrs. Lavinia Stewart had given a $60,000 grant to the University of Arizona. It was the largest private grant that the university had received up until that point.
The observatory was built in a distant corner of the empty campus. Construction, interrupted by World War I, took nearly 4 years. Once the observatory was complete, the telescope arrived on campus in pieces, hauled from the train yard on horse-drawn wagons.
Douglas is the architect who designed the building. He's the one that decided the size and scope of the telescope, and he would also decide on the scientific program to begin with at the observatory.
Douglas and Southern Arizona now had their observatory. The first public evening was held in September of 1922.
He opened the observatory to the general public because he wanted them to share in the wonders that were to be discovered by his telescope.
Science was to change dramatically in the years following the dedication of Stewart Observatory. Those changes were driven by the new global realities following World War II and the ensuing Cold War. Astronomy changed as well. Stewart Observatory and Southern Arizona would play a prominent role in the many developments to come.
To watch the full documentary Focusing the Universe and all of the documentaries we're featuring in this episode, visit azpm.org/100 years. To achieve a comprehensive understanding of space requires mastering a wide variety of academic disciplines, including astronomy, astrophysics, and geology. The University of Arizona has long been on the cutting edge of that multifaceted approach. The Lunar and Planetary Laboratory at the U of A was established by Gerard Kuiper, the man who, among other things, discovered new moons around Uranus and led the effort to create a photographic lunar atlas, later used to select landing sites on the surface of the moon.
With data for the atlases pouring in, Kuiper's students scrambled to interpret what they were seeing. It was clear that in order to understand the moon, the Lunar and Planetary Laboratory would have to broaden its scientific expertise beyond astronomy to geology.
Kuiper had realized, even before I went to Yerkes, that by gosh, we really need to be doing geology too.
But the only degrees available to Kuiper's students came from the university's astronomy department.
The astronomy department, which was tiny in those days, was one guy, Carpenter. And he didn't like Kuiper, and he didn't like any of us who were with Kuiper. And I wanted to be able to take some geology courses for my degree, and he said, you can do all you want, but they're not going to count. You have to get a degree in astrophysics. And I said, well, I don't want a degree in astrophysics.
And so there was kind of a gulf between the Stewart Observatory and Lunar and Planetary Lab. That has gone away and melted away with the discovery of extrasolar planets and the formation of planetary systems.
The missing geology link would come from Flagstaff, Arizona, where Dr. Gene Shoemaker established a branch of the United States Geological Survey called astrogeology. Shoemaker's team was creating geological maps of the moon. Some were based on images from the Lunar and Planetary Lab's photographic atlases. Shoemaker came to the University of Arizona and enlisted the help of Dr. Spencer Titley, a geology professor.
Gene Shoemaker came down to the department in, I believe, 1962 or 63, and talked about his new branch of astrogeology. He asked if I'd like to become part of it. I said, sure.
Titley became a mentor to Kuiper's students. The seeds of a multidisciplinary approach to planetary science were being sown.
Spence Titley took us really under his wing, just voluntarily.
He said, look, I don't know what you guys need to take, but you're welcome to come over in geology and take whatever you think. You can take astronomy courses and geology courses, whatever mixture you want.
I took the three of them and retreaded them as geologists.
In the years to follow, planetary geology would become a critical component of how we study other worlds. In 1964, NASA sent a contingent of astronauts to Kitt Peak Observatory for a first-hand look at the moon. Spencer Titley became the future moonwalker's personal liaison during the visit. He recalls watching astronaut Ed White arrive in a fighter jet at Tucson's Davis-Monthan Air Force Base. White was dressed appropriately for the desert.
I remember Ed White climbed out of his F-102, reached in, grabbed a cowboy hat, put it on.
Just a year later, White became the first American to take a walk in space.
Okay, I'm separating from the spacecraft.
Okay, separate from the spacecraft at this time. All right.
Okay, my feet are out.
NASA was learning how to live and work in Earth orbit. But the moon remained a distant target, visible only through the telescope. It was time for a closer look. NASA's Jet Propulsion Laboratory in Pasadena, California, prepared 3 series of robotic spacecraft to visit the moon ahead of the astronauts: Ranger, Surveyor, and Lunar Orbiter. First up was the Ranger program. The plan was simple: equip the spacecraft with television cameras and crash land them into the moon, providing the first up-close look at the surface. The scientists behind Ranger included a who's who list of Southern Arizona lunar experts.
Dr. Shoemaker, Mr. Whitaker, and the principal experimenter, Dr. Kuiper.
But the program was beset with problems. Engine failures left Ranger 1 and 2 stranded in Earth orbit. Ranger 3 and 5 missed the moon entirely, and Ranger 4 lost guidance and smashed into the far side of the moon. The situation was becoming desperate.
Ranger 6 was going to work. I mean, if it didn't, heads were going to roll.
Ranger 6 was a perfect spacecraft launch, perfect separation of the boosters, perfect landing exactly where it was supposed to hit on the moon. Everything was perfect except the camera would not turn on.
No pictures, and so boy, people were unhappy.
So Ranger 7 then, it really put NASA's future on the line, the whole lunar program on the line.
NASA awarded the Phoenix Mars mission to the University of Arizona in 2003. It was the first ever to be headquartered at a public university. The mission was designed to land a spacecraft in the northern plains of Mars to look for water ice beneath the planet's surface. After a series of failed attempts, Phoenix was aptly named, rising from the ashes of those previous missions.
Phoenix's first chance to escape this planet is now less than 9 hours away.
We're in final preparations for what we call the Mobile Service Tower rollback. And this is the structure that surrounds and protects the rocket leading up to launch. Actually pulls back so that the rocket is left on the pad so it can launch into space. If everything goes well, it's about a 30-minute process. It'll pull back about 10 yards and stop to make sure everything's cleared, and it'll pull back all the way. It's kind of like Christmas morning, you know. You think in your mind what it's going to look like when you put the rocket with the boosters, with the spacecraft all together, and it's another thing to see it pulled back and you have this brand new sparkling rocket with this payload that's brand new, ready to go into space and do great things.
This is the culmination of 4 years of hard work. It feels great. I have utmost confidence in our team, in the ULA team that built the launch vehicle, and we are ready to go. We're going to Mars.
We'll launch at about 5:26, so I think about 3 a.m. the last person will be out here, and the closest person at that point will be about 1.2 miles away.
I'm in the control room, along with the rest of my team, and we're doing the countdown, and you know, if anything happens to go wrong, we'll be consulting on what to do. But if everything goes right, I don't have much to do at all. I'm going to run outside the building and watch it actually face-to-face rather than on TV.
verify area weather conditions or go for launch.
Weather is go.
This is the LTD on Channel 1. The following personnel report ready to proceed with the countdown.
Morning. How are you?
Very well. How are you?
I'm fantastic.
Report ready to proceed with the countdown and remain.
You go up there and you see this whole tower and you don't even see the rocket. And then this thing, it's like this, you know.
Ready. And launch director.
Ready.
5, 4. Main engine start. 2, 1.
Oh, waiting a long time for this. Long time. Look at that. Go!
How's it feel now?
No words. I got no words. It's unbelievable. I think what's next is a little party.
Wow. There you go.
We gotta learn how to run this thing now. Now that it's off the ground. Been spending months and months and months just getting everything working, waving goodbye. But this is gonna be a tough thing to run.
Oh, it was fantastic. 4 years of hard work, and we finally see it to go off and head off to Mars. It's just incredible.
Congratulations.
It was great. It was a beautiful light show. I mean, it was everything. The best launch I've ever seen.
It's so fun. It's too bad Peter's not here, but I know he's celebrating.
Let's go.
All right.
Another launch, not quite as important. We got to wait about another hour before we know that everything is good, because that's about when we start talking to the spacecraft. But it feels good. It feels great.
Tiga.
Tiga. Hey, hey, hey.
Well, you don't see airplane contrails for that.
No.
An anxious world awaits news from the Phoenix, delivered by a team now themselves much less anxious than they were just hours before.
Well, there's a lot of smiles around this center and around the country today. Pretty exciting morning. Phoenix has left Canaveral Air Force Station. The next stop is Mars.
It's pretty cool. It doesn't get any better than this when you're in this business, to put a spacecraft up and then wait for it to call home and have it respond the way it did. So we're all thrilled.
It's 295 days for our entry, descent, and landing, where we get to do everything that was done today, but we do it in reverse. We go from the velocity we're in now down to 5 miles an hour in 7 minutes. Be a lot of fun. Come see us in JPL on May 25th.
From the position I was in, it was headed directly towards Mars, which was near the Pleiades. The exhaust gases from the solid rockets were still there in a cloud, and the cloud was slowly being pulled by the winds. This cloud turned into what looked like wings and a beak and a long tail, and looked amazingly just like a phoenix bird. The message to me was, the phoenix bird has risen.
Before Phoenix could begin its scientific mission, it first had to land safely on the surface of Mars. To do that, the spacecraft would have to survive entry, descent, and then landing. 7 minutes of terror that began on May 25th, 2008.
We had a vision back in February of 2002. Let's follow up on this great new discovery by the Odyssey orbiter that there's ice in the polar regions. But following up, the quickest we can do it is 6.5 years. That's a long wait. You see, my hair's gone gray. I'm turning into an old man while I'm waiting for this mission to happen. So now it's coming up, I'm ready. And it's been hard to wait so long. There's a lot of passion that goes into this mission. We had a kind of a debriefing last night at the end of our training period, our dress rehearsal.
And I was telling people, this is a once-in-your-life adventure we're on, and accept that experience with your full heart, because, you know, it's not going to happen again. We only land on Mars once, and that is a thrilling adventure. Get involved and just feel every moment of it, because don't sit in the back and pretend it's not happening or that it's just another test. This is real.
Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and we're about 77 hours right now from that sequence known as EDL.
We're having a press conference tomorrow to talk about the health of the spacecraft.
As we sit here today, it's really very humbling what we've gone through the past 5 years.
Hopefully the whole world is watching with us, because this is really a mission about the world community going to Mars. That's the way I look at it.
Are we going to see the northern plains in those first pictures, or are we going to be just seeing solar panels?
Today we are 1 day away from the entry into the Martian atmosphere and the descent and landing at the North Polar region of Mars.
If we land successfully and if we're able to do the science that we've designed into this mission, I have every expectation that we'll be able to rewrite the textbooks.
Go where there is no path and leave a trail for others to follow. That's what Phoenix is doing tomorrow.
It doesn't get any more exciting than this.
Welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and thank you for joining us for today's final pre-landing briefing for the Phoenix mission to Mars. I'm Veronica McGregor.
The sky's clear. We've been watching the weather. Everything is set for us. Have a sunny day. The rest of the day is just watching and waiting.
Atmospheric entry on my mark. 5, 4, 3, 2, 1, mark. Expected peak heating rate in 1 minute and 40 seconds. Standing by for a possible plasma blackout.
For those in another room, the question was, is what's going to happen to the lander, I guess, after the mission's over, and whether wind and other things might move it around.
So it takes us 8 hours to get up to 12,700 miles an hour, and then we have 7 minutes to take that velocity down to 0.
You'll see him scream, and you'll probably see me scream, and then I'll run off and get some champagne.
At this point in time, Phoenix goes normally through peak heating. We still have a signal via Odyssey, standing by for reacquisition via direct to Earth.
There's no second chance. There's no, we're not going in an orbit or anything. We're going straight in, and that's our fate.
Stop of Odyssey canister data and switch to 32K in 10 seconds. Standing by for expected parachute deployment. Parachute deployment trigger detected. Heat shield trigger detected. Ground relative velocity 90 meters per second. Land leg deployment trigger detected. Ground relative velocity 60 meters per second. Standing by for altitude conversion. Radar reliable. Altitude 2,000 meters. Altitude convergence detected. Altitude 1,800 meters. 1,700 meters. 1,600 meters. Standing by for land separation. Altitude 1,100 meters. Altitude 1,000 meters. The separation detected. We have verified the signal. Gravity turn detected. Altitude 600 meters. 500 meters. 400 meters. 250 meters. 150 meters. 100 meters. 80 meters. 50 meters. Come on. Constant loss of space detected. Altitude 40 meters. 30 meters. 20 meters. 50 meters. Standing by for touchdown. Touchdown signal detected. Land init sequence initiated. Phoenix has landed. Welcome to the northern place of Mars.
The latest exploration mission, headquartered at the University of Arizona, is the OSIRIS-REx asteroid sample return mission, which launched on September 8, 2016. On Friday, September 22nd at 9:51 a.m., the spacecraft passed within 11,000 miles of Earth, using its gravity like a slingshot to propel toward the asteroid Bennu. While in the neighborhood, many of the instruments were used to study our planet before the spacecraft arrives at its target in August of 2018. Now, here's what it looked like when the first pictures of Earth were sent back to the scientists at the Mission Control Center a few hours later.
Right there, this is Hawaii.
Yeah. Oh, that's so great.
Right there, this is Big Island, Maui, Oahu.
That's great. We took 138 images yesterday afternoon. They're all listed here. And basically, you have the name, the time, you know, something about an ID, and something about what was being imaged, and which camera it was, and the commanded exposure time. All that stuff is in here. And it just makes a handy-dandy reference.
Yeah, we haven't color corrected yet. No, this isn't actually that bad. Land masses are brown, or they look pretty red. And then here, and then the ocean is blue. Yeah. So
Clouds are white. Did you see Tucson?
Yeah.
Isn't that cool?
I did not see Tucson.
Well, I mean, you can see the desert Southwest.
Okay.
And,
Is this, yeah, so is this Tucson? Yeah, let's see. Yeah. There's the Baja.
we'll just have to see. I'll compare them after the fact.
Excited?
Oh, yeah. No, it was, I mean, you know, we designed, we built, we launched a camera. It went around the sun once, and then it took a picture of our home planet. I mean, what more do you want? Yeah. It's really cool. Yeah. And it's going to do really good at Bennu.
Right.
I mean, I really feel like, you know, we've tested it at the really long exposure limit with all the stars. We've tested it at the really short exposure limit with this. It works at both limits with some effort, but it works at both limits. Right in their middle is the sweet spot. This is where Bennu is, right?
That's cool.
Yeah.
All right. And Australia down here?
Yeah,
Right?
I think so.
Yep.
To watch the full documentary, OSIRIS-REx Countdown to Launch, and all of the documentaries we featured in this episode, visit azpm.org/100years. Thank you for joining us here on Arizona Illustrated. I'm Tom McNamara. See you next week.